When people talk about semiconductor, they talk about chips, but insiders know the real bottleneck is not chips. The real bottleneck is the machines that make the chips. A single advanced chip factory costs over 20 billion US dollars to build, but without the right equipment, that factories produce nothing, not slower chips, nothing at all. An advanced semiconductor fabrication plant is not one machine. It is a network of the hundreds and sometimes thousands of ultra precise machines. These machines include lithography systems, they include etching systems, they include the diaprization system, they include ion implantation tools, they include metrology systems, they include inspection system. They also include packaging equipment. Each step requires a different specialized equipment. If one link is missing, the entire production line stops. The global semiconductor equipment market is dominated by only a few companies. Lithography equipment is led by NASMO in the Netherlands. Etching and deposition equipment are dominated by Applied Materials in the United States. The etching and deposition are also dominated by Lam Research in the United States. Process control and inspection system are dominated by KLA in the United States. Advanced packaging and testing equipment are led by Tokyo Electro in Japan. Advanced packaging and testing equipment are also supported by Screen in Japan. These companies form the backbone of global chip manufacturing. Together, a small number of firms control the majority of advanced semiconductor equipment supply. A single advanced chip may go through more than 1,000 processing steps. And each step requires a nanometer level precision. Each machine must operate continuously 24 hours a day. And each machine must operate with a near zero tolerance for error. If one critical machine stops, the entire production line stops. The loss per day for an advanced semiconductor fabrication plant can reach $5 to $10 million. Many people assume that if you can design chips, you can build the equipment. This assumption is not true. Semiconductor equipment often requires even higher precision than the chips themselves. For example, etching machines must curve patterns just a few nanometers wide on silicon wafers. These patterns must be curved without damaging the surrounding structures. The tolerance is smaller than the width of DNA. Achieving this level of precision requires advanced materials. It requires ultra stable power systems. It requires precision optics. It requires high end software. It also requires decades of engineering refinement. Leading semiconductor equipment companies have built their expertise over 30 to 50 years. Their technologies are the result of continuous iteration. They rely on millions of hours of accumulated process data. They also depend on deep integration with chip manufacturers. Developing a new advanced tool can take 10 to 15 years. It may require billions of dollars in research and development. It also requires extensive real world validation. Even after development, the tool must prove its reliability. It must prove its yield performance. It must prove its cost efficiency. It must prove long-term operational stability before fabrication plant will adopt it. A semiconductor fabrication plant is not flexible. Then once a production line is celebrated for certain machines, switching equipment become extremely risk. This is because any tiny variation in the process can reduce yield. If yield drops by even 5 to 10%, the fabrication plant may lose profitability. For this reason, chip makers prefer proved equipment with decades of track record. This creates a powerful locking effect within the semiconductor industry. The semiconductor equipment industry is worth more than $100 billion annually. However, its influence is far greater than its size. This is because whoever controls the equipment influences who can produce advanced chips, and whoever produces advanced chips influences artificial intelligence. And it influences supercomputing. It influences defense electronics. It influences autonomous system. It influences next generation communications. This is upstream controls of the digital world. A modern fighter jet contains millions of lines of software code. It also contains thousands of semiconductor chips. A modern data center contains tens of thousands of processors. An electric vehicle contains thousands of semiconductors. All of these technologies depends on chips, and the chips depend on equipment. So the real point becomes this: who controls the tools that build the digital age? Most people see smartphone, few people see chips factories. Almost nobody sees the machines inside those factories. But those machines quietly define who can manufacture the future. They do not define it through headlines. They do not define it through slogans. They define it through engineering.